Hi folks, welcome to your third video in your 10.4 lecture series. And in this video, we're going to take a look at approximating definite integrals with a maximum allowable error. Okay, so we're going to put together a lot of things that we've learned in chapter 10, all in the same problem. All right, example 4 says, approximate this definite integral from 0 to 1 of e to the negative x squared dx with a maximum error of 0.005. All right, so we're going to break this down into 3 digestible steps. All right, the first thing we're going to do is we're going to use our good old table number 1 and the idea of substitution. Okay, so I know that g of x, which is in our table, is e to the negative x, which equals 1 minus x plus 1 over 2 factorial x squared minus 1 over 3 factorial x cubed, plus it keeps going. You end up with negative 1 to the n over n factorial x to the n. Okay, so we're just copying that straight off of our table. Now, we want to substitute everywhere we see an x, we're plopping in an x squared. Okay, so g of x squared means we have e to the negative x squared. All right, we've got 1 minus x squared plus 1 over 2 factorial x squared squared minus 1 over 3 factorial x squared cubed plus, okay, negative 1 to the n over n factorial and then x to the 2n because it's going to be x to the n squared. Okay. And this, again, is just like writing out a few of the terms, but not all of them. Okay, so if we clean this up a little bit, we've got 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 6 factorial. And we can go all the way to negative 1 to the n over n factorial times x to the 2n. Okay. All right, well, a couple things to note here. We have an alternating series, positive minus, plus minus, plus minus, and the coefficients are getting smaller and smaller and smaller as we go along. That's going to allow us to use the shortcut that we did in the second video, okay? So now before we get there, we need to integrate. All right, so I know that my integral is going to be the integral of e to the negative x squared dx. And I'm not going to put in my bounds quite yet because I want to just like do the integral and then I can plug in my numbers after. Okay. So this is the integral of, instead of writing e to the negative x squared, I'm going to replace it with the series that I have, okay? So 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over, oh gosh, that's not 6 factorial, that is 3 factorial, excuse me, 3 factorial plus until I get to negative 1 to the n x to the 2n over n factorial. And the number of terms that I go to is going to be dependent on what my error is, okay? So the bad news is we kind of got to write them all out, at least for the beginning. But once we get to the plugging in step, that's when we'll be able to say, oh, I only need 4 terms and I can cut it here because this is the error that I'm looking for, okay? All right, now when we integrate, we know we always start with a c, and now we're going to integrate each term at a time. So the integral of 1 is x. The integral of x squared is x to the 3rd over 3. Then the integral of x to the fourth over 2 factorial is x to the fifth over 5 times 2 factorial minus x to the seventh over 7 times 3 factorial. And I would basically keep going, and I would get my -1 to the n. That has to stay because I'm alternating my signs. But I know that on the bottom, I'm going to have 2n plus 1 times my n factorial x to the power plus 1. Okay? All right. So I've written out a bunch of terms. I've taken my integral one at a time. And now I'm going to evaluate. Okay? Okay, what do I mean by evaluate? I mean that the integral from 0 to 1 of e to the negative x squared dx is going to equal f of 1 minus f of 0, because those are my bounds. So what that means is I need to plug 1 in everywhere I see an x, and then I'm going to plug in 0 everywhere I see an x, and I'm going to subtract the two and see what we get. Okay, well, we're going to get c plus 1 minus 1/3 plus 1 over 5 times 2 factorial is 10 minus 1 over 7 times 3 factorial, whatever that is, plus -1 to the n over 2n plus 1 n factorial times 1 to the 2n plus 1. Okay, so that's what I get when I plug in 0. But when I plug in 1, excuse me, but when I plug in 0, everything is going to go to 0 except for my c. So we've got a c here. Okay. Now, let's think about this. We are subtracting the second one from the first one. So c minus c, those are going to cancel out, and I'm just going to be left with the terms in here. So now my question is, how many of these terms do I need? And I'm just going to keep going until I get a term that is smaller than 0.005. Okay, so let's see how many we need. I've got 1 minus 1/3 plus 0.1 minus 1 over 42. But when I do the fifth term, I'm going to get 1 over 216. And if I turn this into a decimal, it becomes 0.0046, which is smaller than 0.005. So this is where I get to stop. In other words, the first 4 terms together will give me an approximation of this integral that I wouldn't know how to do otherwise, okay? And when I add those all together, I get 0.743, and so this is my approximate integral, okay? All right, so come on back for the last video. In the last video, we'll take a look at example number 5, which is going to be pretty similar to this one. We're going to use our 3 steps, use our table and sub, integrate, and then evaluate to figure out how many terms we need to approximate this within a maximum allowable error.